simplest place to start applying Newton's laws is to an infinitesimal particle. So we're thinking of an object with mass but no volume. Now, of course, in reality, these things don't exist, but they're a very useful abstraction, and we can treat even extended objects such as baseballs, cats, even planets, as particles in certain contexts. Newton's first law says, for a particle, if there are no forces applied, then its velocity is constant in magnitude and direction. Newton's second law tells us how a particle's velocity will change when there is an applied force. This is the famous F equals ma. And so to think about this, consider, for example, a particle moving at time t with an initial velocity v. And imagine there's a force applied, F, such that at some later time, t plus delta t, the velocity will have changed. The change in the velocity vector, delta v vector, will be the acceleration times the short amount of time, delta t. And according to Newton's second law, that acceleration will be F over m. For large masses, a fixed force F will result in a smaller acceleration. And you can see that here. When m is really, really big, a certain amount of force will only give you a very small acceleration. Of course, Newton's second law is really a differential equation. We're relating a force to the second time derivative of a position vector. If we can consider the simple case of one-dimensional motion, so just motion along the x-axis, and a constant force along the x-axis, F naught, then we can rewrite the differential equation from Newton's second law as x double dot is equal to F naught over m. In other words, that x double dot is a constant, and then we can solve for x as a function of time. A very familiar example of constant acceleration is falling under gravity. Here's a simple plot of the acceleration along the x direction as a function of time. Of course, it's a constant, so it's just a flat line. So we can solve for the velocity along the x direction as a function of time by doing one integration of that equation. Find we get an integral that looks like this. So there's F naught over m integrated against t plus v naught, the initial velocity. If we do that integral, what we find is that a velocity as a function of time is F naught over m times t plus v naught. And so now if we plot the velocity along the x direction as a function of time, it looks like this orange curve. It starts out at v naught, of course, when t is 0, and increases linearly with time. And then finally we can solve for the displacement as a function of time by integrating the velocity over time. We need to incorporate the initial displacement, x naught. When we do that integration, what we find is we get a displacement, x of t, which increases with t squared. Then there's a term v naught times t plus x naught. And so plotting x as a function of time gives you the blue curve there. It's a parabola. The value for x at time equals 0, of course, is x naught by definition. It turns out that Newton's first law actually only holds in the case that we're sitting in an inertial frame. To see exactly what that means, imagine that you're sitting on a train that's not moving, and inside the train car with you is a block of ice that can slide frictionlessly across the train car floor. Of course, if you're both standing at rest, the block of ice will not appear to move relative to you. Nothing is going to happen. Now imagine you're riding in the train car, and you, the train car, and the block of ice are all moving forward with a constant velocity v. In this case, you will also not see the block of ice in motion because you are moving along with the block of ice at exactly the same rate. The distance between you and the block of ice is not going to change as long as you're all traveling together at the same velocity. But now imagine the case that your train car is coming into the station, and so the brakes are suddenly applied, giving the whole train car an acceleration toward the left, so a deceleration. Of course, the block of ice not attached to the train car and able to slide frictionlessly across the floor will suddenly acquire a forward velocity. Now, as far as you're concerned, there's no external force applied to the ice, and suddenly its velocity changes. That's a violation of Newton's first law. However, Newton's first law only applies in inertial frames, and so this tells us that you must be in a non-inertial frame, since there was no obvious outside force applied to the block of ice, even though its velocity changed. So an inertial frame is a frame that is not experiencing acceleration.